In the last lecture, we developed an algorithm, the simplex method, for solving linear programs with as many decision variables as we like and as many constraints as we like. So we developed the simplex method to solve large linear programs. And we saw how the simplex method worked on an example, but the general principles that we developed could be applied to any linear program that you would like. So in this lecture, we're going to do a second example to use the simplex method to solve a linear program. But by no means, this lecture is going to be a repetition of the previous lecture. Namely, as we do the second example to solve a linear program by using the simplex method, we're going to see some other interesting things that could happen when we use the simplex method. So we're going to see some interesting situations in the simplex method when we solve a second example today. So that's the first thing that we're going to be doing today. And at the end of the lecture, there is some common vocabulary that people use when they use the simplex method. So at the end of the lecture, we're going to talk about this vocabulary of the simplex method. It's good to know this vocabulary because if you talk about the simplex method, everybody uses this vocabulary. So it's nice to have a command of this vocabulary. Okay, so the first thing first, let's see the simplex method in action. Let's see the mechanics of the simplex method on a second example. Okay, so let's look at a linear program that looks something like this. In my objective function, I'm maximizing 5x1 plus 3x2 minus x3, subject to the first constraint, 4x1 minus x2 plus x3 is less than or equal to 6, 3x1 plus 2x2 plus x3 is less than or equal to 9, 4x1 plus x2 minus x3 is less than or equal to 3. And my decision variables are all restricted to be non-negative. Good. Okay, so this is the linear program that we would like to solve. So what did we say? If I want to solve a linear program that looks like this through the simplex method, the first thing we do is we express all of our constraints, all of our inequality constraints as equality constraints. And we use flag variables to do that. So let's remember the idea. So let me define W1 to be the amount by which the right-hand side of the first constraint exceeds the left-hand side. So let's define W1 to be the amount by which the right-hand side of the first constraint exceeds the left-hand side. Okay, good. So if I have a feasible solution to my linear program, then the right-hand side of the first constraint is got to be greater or equal to the left-hand side of the first constraint. So if I have feasible solution to my linear program, W1 has to be greater or equal to 0. So now let's say if x1, x2, x3 is feasible to the LP, then W1 has to be greater than or equal to 0. This number has to be greater than or equal to this number. And W1 is defined as the amount by which the right-hand side of the first constraint exceeds the left-hand side. That means that we can replace the first constraint by W1 is non-negative and W1 is defined like this. So we can replace the first inequality constraint by, or we can express the first inequality constraints equivalently as W1 is non-negative and W1 is defined like this. And in this definition of W1, let me take these terms in the parentheses, throw them to the left-hand side. 4x1 minus x2 plus x3, take this to the left-hand side, plus W1 equals 6. So the first inequality constraint is equivalent to non-negative on W1, and W1 is defined like this. First inequality constraint is equivalent to this equality constraint and non-negativity on W1. Let's define the same game on the second constraint. Let's define W2 to be the amount by which the right-hand side of the second constraint exceeds the left-hand side. Good. If I have a feasible solution to my linear program, the right-hand side of the second constraint is going to be greater or equal to the left-hand side. So W2 has to be greater or equal to 0. So if, let's say, x1, x2, x3 is feasible to the LP, then W2 has to be greater or equal to 0. and W2 is defined in this fashion. Good. So that means that we can replace the first inequality constraint by W2 is non-negative and W2 is defined in this way. We can replace the we can replace the second inequality constraint by, second inequality constraint by W2 is non-negative and W2 is defined in this way. So the second inequality constraint is equivalent to W2 is non-negative and W2 is defined in this way. So throw these guys in the parentheses to the left. Let's write the definition of W2 like this. Good. The second inequality constraint is equivalent to non-negativity on W2 and this equality constraint. And similarly, let's define W3 to be the amount by which the right-hand side of the third constraint exceeds the left-hand side. And with the same logic, we can write the second inequality constraint equivalently as, W3 is non-negative, and W3 is defined as this minus that. So let's put these terms in the parentheses to the left. Good. So my first inequality constraint is equivalent to this equality and non-negativity on W1. My second inequality constraint is equivalent to this equality constraint, non-negativity on W2. My third inequality constraint is equivalent to this equality constraint and non-negativity on W3. So then we can write our linear program as a linear program with all equality constraints. Keep the objective function as it is. Okay. Keep the objective function as it is. And instead of the first inequality constraint, I'm going to use this equality constraint and non-negativity on W1. Okay. Instead of the second inequality constraint, use this equality constraint and non-negativity on W2. This equality constraint and non-negativity on W2. And lastly, instead of the third inequality constraint, use this equality constraint and non-negativity on W3. And I have the non-negativity constraints on my original decision variables. We still need to keep them. Good. So now this linear program that I wanted to solve is 100% perfectly equivalent to this linear program with all equality constraints and non-negative constraints on my original decision variables, as well as these new select variables that we created. So instead of solving this linear program, we're going to attack this linear program. So that is our first job when we solve a linear program through the simplex method. We write down all of our inequality constraints as equality constraints. The next thing we do is we express our linear program as a system of linear equations. We express our linear program as a system of linear equations. Let's do that. Here's my linear equation for the objective function. Let's set the value of the objective to be some variable z. So here's the equation corresponding to the objective function. And I'm going to have one linear equation corresponding to each one of the constraints. Good. This system of linear equations captures all of the information that we have on the linear program that I would like to solve. It has the objective function. It has all of the constraints. Here in the system of linear equations, we do not explicitly write down the constraint that our decision variables are non-negative, but we always keep it in the back of our minds that our decision variables are also restricted to be non-negative. X's are non-negative and W's are non-negative. Okay, so then our simplex method is going to work with this kind of systems of linear equations. Good. So now, here's the most interesting observation. This system of linear equations has such a peculiar structure that it's very easy to read a solution to the system of linear equations. In particular, in this system of linear equations, there are 3 decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. In particular, in the system of linear equations, there are 3 decision variables, W1, W2, and W3, such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. And because of that very peculiar structure, it's very easy to read a solution to this system of linear equations. What is the solution that we quickly read to the system of linear equations? Set W1 to be 6, W2 to be 9, W3 to be 3. Set X1, X2, X3 to be all zeros. If X1, X2, X3s are all zeros, set Z to be 0 as well. So then this is going to satisfy W1 is 6, X's are 0, this is satisfied. W2 is 9, all the X's are 0, this is satisfied. W3 is 3, all the X is 0. This equation is also satisfied. So because I have 3 decision variables, such that each one of these decision variables appears in a different constraint row, it's very easy to read a solution to the system of linear equations. Let's write that solution that we read. W1 equals 6, W2 equals 9, W3 equals 3. All the X's we set to 0, and if X are all set to 0, then Z has to be equal to 0 so that we satisfy the first equality. Good. So again, this linear system of equations has a very nice structure. There are 3 decision variables such that each one of them appears in a different constraint row with a coefficient of 1. Because of that, it is very simple to read a solution to this system of linear equations. Good. And that is the solution that we read in that very easy fashion. So now, is this solution feasible to the linear program that we would like to solve? Is this solution feasible to the linear program that we would like to solve? Here's my linear program with the inequality constraints. X1, X2, X3s are all zeros. 0, 0, 0, 0 is less than or equal to 6, so this constraint is satisfied. 0, 0, 0, 0 is less than or equal to 9, this constraint is satisfied. 0, 0, 0, 0 is less than or equal to 3, this constraint is satisfied. All my x's are 0, so they're greater than or equal to 0, these constraints are also satisfied. So this solution that I read very quickly from the system of linear equations is also feasible to the linear program that I would like to solve. Good. So now from the system of linear equations, we quickly read a solution that happens to be feasible for the linear program that we would like to solve. And furthermore, what is the objective value provided by the solution? X1, X2, X3 are all zeros. So then read the objective value. X1, X2, X3s are all 0, 0, 0, 0. The objective value is 0. It turns out that the value of the Z variable reads the objective value provided by the current solution. Okay. We can also check that this solution that we read is feasible to the version of the linear program with the equality constraints. All the x's are 0, W1 is 6, 0 plus 6 equals 6. All the x's are 0, W2 is 9, 0 plus 9 is 9. All the x's are 0 and W3 is 3, 0 plus 3 is 3. So all of these constraints are satisfied, and all my x's and the w's are non-negative. So this solution is also feasible to the version of the equality constraint linear program that I would like to solve. Good. So then from this system of linear equations, we quickly read a solution. So now here's how the simplex method works. Let's think about that. Let's remember that. Here's how the simplex method works. What we're going to do is, starting from this feasible solution, we're going to apply row operations to the system of linear equations to get to other feasible solutions that give us better and better and better objective values. Applying row operations on a system of linear equations is completely benign. It doesn't change the system of equations that we have on hand. So then starting from this solution, we're going to apply row operations to the system of linear equations to get to other feasible solutions to my linear program that gives us better and better and better objective values. Okay? But the important thing is, as we do those row operations, we're always going to make sure that there will always be 3 decision variables, such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. So we will always maintain that structure. We'll always maintain a structure that there will always be 3 decision variables, each appearing in a different constraint row with a coefficient of 1 and nowhere else. So let's write down some of the observations that we made. First of all, this solution is feasible to the linear program that we would like to solve. This solution is feasible to the LP, giving the objective value 0. Good. So what we're going to do is we're going to apply row operations to this system of linear equations to get to other feasible solutions that give us better and better objective values. We will apply row operations to the system of equations to get to other feasible solutions that give better and better objective values. Good. But as we do so, we will always make sure that there are always going to be 3 different decision variables. There are always going to be 3 different decision variables, such that each one of them appears in a different constraint row with a coefficient of 1, nowhere else. As we apply row operations, we will make sure that we will always have 3 decision variables such that each of the 3 decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. Good. So that's how the simplex method works. So now let's start from the system of linear equations. Let's apply row operations to get to better and better feasible solutions. Let me copy that system of equations right over here. So if x1 plus 3x2 minus x3 equals C, first constraint row, second constraint row, 3x1, 2x2 plus x3 plus w2 equals 9, 4x1 plus x2 minus x3 plus w3 equals 3. And what is the solution that we read? Those are 3 decision variables appearing in different constraint rows with coefficients of 1. So the solution we read is w1 equals 6, w2 equals 9, w3 equals 3, x's are 0. And if my x's are 0, z is going to be 0. Okay. So now I want to get to a better feasible solution. I want to get to a better feasible solution. I want to get to a better feasible solution. So now we're going to look at to answer that question, to get to a better feasible solution, we're going to look at the objective function row. In the objective function row, if I increase the value of the decision variable x1, for each unit of increase in x1, the objective function is going to go up by 5. So it's a good idea to increase the value of x1 if I want to get to a better objective value. Again, in the objective function, for each unit of increase in x2, the objective function is going to go up by 3 units. It's actually a good idea to increase the value of x2 as well, if I want to get to a better objective value. But on the other hand, the coefficient of x3 is over here is -1. For each unit of increase in x3, the objective function is going to go down by 1 unit. So if I want to get to a better objective value, if I want to increase the value of my objective, increasing x3 is not a good idea. So then if I want to increase the value of my objective, I want to increase the value of x1 or x2. It looks like for each unit of increase in x1, my objective goes up by 5 units. For each unit of increase in x2, my objective goes up by 3 units. It looks like x1 is giving me a bigger bang for the buck. For each unit of increase in x1, I get 5 units of increase in the objective function. So let's go ahead and increase x1. If you went ahead and increase x2, you're still gonna get to the optimal solution. But again, heuristically, as a rule of thumb, I'm gonna increase the decision variable that gives me bigger bang for the buck. So let's say we're gonna increase the value of x1. So then the next question we're asking ourselves, how much can we increase x1 without violating feasibility of the solution on hand? How much can we increase x1 without violating the feasibility of the solution that we reach? In order to answer that question, we're going to look at our constraints. So let's look at our constraints. Let's look at the first constraint. So right now we're increasing the value of x1. Right now x1 is 0, w1 is equal to 6. Right now x1 is 0, w1 is equal to 6. x1 is 0, w1 is equal to 6. So I'm increasing x1. The question I'm asking myself, how much can I increase x1 without violating the feasibility of the current solution on hand? Right now x1 is 0, w1 is equal to 6. As I increase x1, I'm going to eat up the increase in the value of x1 by decreasing w1. Right? So right now x1 is 0, w1 is equal to 6. I'm going to eat up the increase in x1 by decreasing w1. So right now x1 is 0, w1 is equal to 6. If I increase x1 to 1, then this is going to be a 4. w1 has to come down to 2 so that they're going to still add up to 6. If I increase x1 to 6 over 4, then this is going to be equal to 6. Then w1 is going to be equal to 0 so that they add up to 6. If I increase x1 to just a little above 6 over 2, this is going to be greater than 6. So then w1 has to be negative so that they add up to 6. So the largest I can increase x1 so that w1 still doesn't turn negative is 6 over 4. So from the first constraint, we can increase x1 up to 6 over 4, which is 3 over 2, before w1 turns negative. Good. This is from constraint 1. What's happening in constraint 2? I'm increasing the value of x1. Currently, x1 is at 0 and w2 is at 9. x1 is at 0, w2 is at 9. As I increase the value of x1, I'm going to make up for the increase in x1 by playing around with w2. Okay, so right now x1 is 0, w2 is equal to 9. If I increase x1 to 1, this is going to be 3. So then w2 has to come down to 6 so that they still add up to 9. If I increase x1 to 2, this becomes 6. W2 has to come down to 3 so that they add up to 9. If I increase x1 all the way up to 3, so this becomes 9, W2 is going to be equal to 0. If I increase x1 a little bit above 3, so let's say it's 3.1, this becomes 9.3. W2 has to be equal to minus 0.3 so that they add up to 9. In that case, W2 becomes negative, so I go into infeasibility. So the largest I can increase x1 before W2 turns negative is 9 over 3. So 9 over 3 is 3 before W2 turns negative. And what's happening in the third constraint row? Right now in the third constraint row, x1 is 0, and I'm increasing x1, w2 is equal to 3. As I increase x1, I'm going to make up for the increase x1 by playing around with w3. Right now, this is 0, this is 3. If I increase x1 all the way over to 3 over 4, then this is going to be 3. 4 times 3 over 4 is 3. Then w3 is going to be equal to 0, and that is the largest x1 can go before w3 turns negative. From the third constraint row, we can increase x1 up to 3 over 4 before w3 turns negative. So the first constraint row says you can increase x1 all the way to 3 over 2 before you get in trouble. Second constraint says you can increase x1 all the way to 3 before you get in trouble. Third constraint says you can increase x1 all the way to 3 over 4 before we get in trouble. So then what is the largest we can increase x1 to before we get in trouble? As soon as we increase x1 all the way to 3 over 4, then we're going to start getting in trouble. So the largest we can increase x1 up to is 3 over 4. So we can, well, let's say we increase x1 up to the minimum of those three so that we don't get in trouble. 3 over 2, 3 and 3 over 4. And the minimum of them is 3 over 4, 0.75. We're going to increase x1 all the way up to 3 over 5. If you do so, the binding value for x1 appears in the third constraint. So the new value of x1 is going to be determined by the third constraint, which means that we're going to do row operations so that x1 appears only in the third constraint row with a coefficient of 1 and nowhere else. Okay, so we're going to increase x1 here. X1 from the first constraint, we can increase x1 all the way to 3 over 2 before we get in trouble. Second constraint, we can increase x1 all the way to 3 before we get in trouble. Third constraint, we can increase x1 all the way to 3 over 4 before we get in trouble. So the largest we can increase x1 before we get in trouble is 3 over 4. If we increase x1 to 3 over 4, the new value of x1 is determined by the third constraint. So we're going to do row operations such that x1 appears only in the third constraint with a coefficient of 1. Okay, we're increasing x1 to 3 over 4. The new value of x1 is determined by constraint 3. So do row operations such that x1 appears only in constraint 3 with a coefficient of 1 and nowhere else. Great. So let's do those row operations such that x1 appears only in the third constraint row with a coefficient of 1, nowhere else. So I want x1 to disappear from the objective function row. That means that if I take the third constraint row, multiply it by minus 5 over 4, 4 times minus 5 over 4 is going to give me 5. So that's going to cancel the 5 in the objective function. So I want to multiply the third constraint row by minus 5 over 5, add it to the objective function row. Likewise, if I want x1 to disappear from the first constraint row, take the third constraint row, multiply it by minus 1, add it to the first constraint row. And if I want x1 to disappear from the second constraint row, take the third constraint row, multiply it by minus 3 over 4, add it to the second constraint row so that x1 disappears from the second constraint row as well. Let's do those row operations. Good. Let's take care of the objective function row. 4x1 times minus 5 over 4 minus 5x1 plus 5x1. That gives me 0x1. x1 disappears from here. That's what I want anyway. Minus 5 over 4 times x2. That is minus 5 over 2x2 plus another 3x2. 3 minus 5 over 4. That is going to give me 12 over 4 minus 5 over 4. That is 7 over 4 x2. Let's keep going. Minus 5 over 4 times minus x3. That's plus 5 over 4 x3 minus another x3. 5 over 4 minus 1. That is 5 over 4 minus 4 over 4. That is 1 over 4 x3. No w1 here times minus 5 over 4 is 0 w1 times minus 5 over 4 is 0 w1 plus another 0 w1, 0 w1 here. 0 w2 here times minus 5 over 4 is 0 w2 plus another 0 w2, no 0 w2 here. w3 times minus 5 over 4 minus 5 over 4 w3 plus another 0 w3 minus 5 over 4 w3. Good. And on the right-hand side of our objective function row, z, 3 times minus 5 over 4 is minus 15 over 4. So z minus 15 over 4 in the objective function row. Let's keep going. Let's take care of the first constraint row. Multiply the last constraint row by minus 1, add it to the first constraint row. 4 times minus 1 is minus 4x1 plus 4x1, 0x1, x1 goes away. That's what I'm after anyway. 1x1 times minus 1 is, 1x2 times minus 1 is minus x2. Minus another x2, minus 2x2. Minus x3 times minus 1 is plus x3, plus another x3, 2x3. 0 w1 times minus 1 is 0 w1, plus another w1, w1. No w times minus 1 is no w2, plus another no w2, no w2 here. w3 times minus 1 is minus w3, plus 0 w3, minus w3. On the right-hand side, 3 times minus 1 is minus 3, plus another 6, 6 minus 3, That's going to be a 3 on the right-hand side. Let's take care of the second constraint. Multiply the third constraint row by minus 3 over 4, add it into the second constraint row. 3 times minus 3 over 4 x1 is minus 3x1. I'm sorry, let's say it again. 4x1 times minus 3 over 4. 4x1 times minus 3 over 4 is minus 3x1 plus another 3x1, 0x1. That's what I wanted anyway. x2 times minus 3 over 4 is minus 3 over 4x2 plus another 2x2, 2 minus 3 over 4. 2 minus 3 over 4. That is 8 over 4 minus 3 over 4. That is 5 over 4, x2. Good. Minus x3 times minus 3 over 4, 3 over 4 x3, plus another x3, 1 plus 3 over 4. That is 4 over 4 plus 3 over 4. That is 7 over 4. No W1 plus no W1, that is 0 W1. 0 W2 times minus 3 over 4 is 0 W2 plus another W2. That's a W2 here. Good. W3 times minus 3 over 4, minus 3 over 4 W3 plus 0 W3. On the right-hand side, 3 times minus 3 over 4 is minus 9 over 4 plus another 9. 9 minus 9 over 4. So 9 is 36 over 4 minus 9 over 4. That is going to be a 27 over 4. Great. Okay. And lastly, we want x1 to appear in the third constraint row. We want x1. You want x1 to appear in the third constraint row with a coefficient of 1. So we're going to multiply the third constraint row by 1 over 4 so that x1 appears here with a coefficient of 1. Good. This is the next system of linear equations that we reach. Question: do we have 3 decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else? Yes. W1, W2, and X1. So then let's quickly read a solution to this system of linear equations. W1 is 3. W2 is 27 over 4. And X1 is 3 over 4. X2, X3, and W3 are 0. If X2, X3, and W3 are 0, then Z has to be 15 over 4 so that we satisfy the first equality. Good. The next question is this solution that we read, feasible to the linear program that we would like to solve? Let's again look at the version with the less than or equal to constraint. X2 and X3 are 0, X1 is 3 over 4. This is 0, this is 3 over 4. 3 over 4 times 4 is 3. So 3 is less than or equal to 6, we're good here. This is 0, X3 is 3 over 4. 3 times 3 over 4 is 9 over 4. 9 over 4 is less than or equal to 9. We're okay here. This is 0, X1 is 3 over 4. 4 times 3 over 4 is 3. That's less than or equal to 3. We're okay here. And all my x's are greater than or equal to 0. Indeed, the solution that we obtained here is also still feasible to the linear program that we're trying to solve. And lastly, what is the objective value provided by the solution? X2 and X3 are 0, 0, 0. X1 is 3 over 4. 5 times 3 over 4 is 15 over 4. So indeed, the value of the Z variable captures the objective value corresponding to the current solution that we have on it. So in the previous iteration, our objective value was 0. Now we increase the objective value to 15 over 4. So we made progress. The next question we ask ourselves is there any decision variable that we can increase to make our objective value even better? To answer that question, we look at the objective function row. For each unit of increase in x2, the objective function goes up by 7 over 4. So I can increase x2 to make my objective value better. For each unit of increase in x3, my objective function is going to go up by 1 over 4. So I can increase x3 to make my objective value better. So there are decision variables that I can increase to make my objective function better. Here, W3, for each unit of increase in W3, the objective function goes down by -5/4. There's a negative sign here. So increasing W3 is not a good idea. So that to get to a better objective value, I'm going to increase either X2 or X3. But the coefficient of X2 is bigger. For each unit of increase in X2, I'm going to get 7/4 units of increase in my objective function. So let's go ahead and increase X2. Let's increase the one that gives us a bigger bang for the buck. So the next question is, how much can we increase X2 before we violate the feasibility of the solution that we have on hand? In order to do that, we're going to look at the constraints. Let's look at the first constraint. So now something interesting is going to happen that we've seen before. So I'm increasing X2. The question I'm interested in is, how much can I increase X2 before I start violating the feasibility of the solution that I have in hand? Let's look at what's happening in the first constraint. Right now, X2 is 0, W1 is 3. Right now, X2 is 0, W1 is 3. As I increase X2, I'm going to make up for the increase X2 by playing around with W1. As I increase X2, I'm going to make up for the increase X2 by playing around with W1. So right now, X2 is 0, W1 is equal to 3. If I increase X2 to 4, this is going to be -8. So then for them to add up to 3, W1 is going to be equal to 11. -8 plus 7 is 3. If I increase X2 to 10, this is -20, then W1 has to be 23, so that they add up to 3. If I increase X1 to 50, this is -100, W1 has to equal to 1/3, so that they add up to 3. If I increase X2 to 1 million, this is -2 million, so that W1 has to be equal to 2 million and 3, so that they add up to 3. So from this first constraint, I can increase X2 as much as I want without W1 turning negative. Okay, and that's happening because X2 appears in this constraint row with a coefficient of -2. It's got a negative coefficient. So then from first constraint row, I can increase X2 as much as I want without W1 turning negative. If I increase X2 to 1000, then this is -2000, then W is going to be equal to 2003, so that they're going to add up to -2000 plus 2003, that's going to add up to 3. So I can increase X2 as much as I want without W1 turning negative. So from the first constraint row, can increase X2 as much as we want without W2 turning negative. Great. What's happening in the second constraint row? Okay, in the second constraint row, I'm increasing X2. I'm going to make up for the increase in X2 by playing around with W2. If I increase X2 all the way up to 27/5, if I increase X2 all the way up to 27/5, so if this is 27/5, 27/5 times 5/4, that is going to be 27/4. Then W2 has to go all the way down to 0, so that they add up to 27/4. So the largest X2 can go up to before W2 starts turning negative is 27/5. If X2 is 27/5, 5/4 times 27/5 is 27/4. So then W2 has to be equal to 0. Okay, so that's the largest I can increase X2 before W2 just starts turning negative. So now from the second constraint row, can increase X2 up to, let me write it like this, 27/4 divided by 5/4, that is 27/5. If I increase X2 all the way to 27/5, 27/5 times 5/4 is 27/4, then W2 has to turn negative. Has to be exactly equal to 0, let me say it that way. So can increase X2 all the way up to 27/5 before W2 turns negative. And by the way, I made a typo over here. From the first constraint, I can increase X2 as much as I want without W1 turning negative. Okay, good. And from the third constraint row, what's going on? As I increase X2, I'm going to make up for the increase X2 by playing around with the X1. If I increase X2, I'm going to make up for the increase in X2 by playing around with X1. Right now, X2 is equal to 0, X1 is equal to 3/4. If I increase X2 all the way to 3, then it's going to be 3 times 1 over 4, 3 over 4. Then x1 is going to be equal to 0 to make sure that they add up 3 over 4. And if I increase x2 above 3, then x1 has to turn negative. So the largest x1 can go up to before x1 turns negative is 3. So let's say can increase x2 all the way up to 3 over 4 divided by 1 over 4. That's a 3 before x1 turns negative. Okay, so now I'm putting those two things together. From the first constraint, I can increase x2 as much as I want without getting trouble. From second constraint, I can increase x2 all the way to 27 over 5. That is like 5.4. From third constraint, I can increase x2 all the way to 3 before I get in trouble. So what is the largest I can increase x2 before I get in trouble? The minimum occurs here, so I can increase x2 all the way to 3 before I get in trouble. So we're going to increase x2 up to the minimum of 27 over 5 and 3, and that is 3. When I increase x2 all the way to 3, the new value of x2 is determined by the third constraint row. So we're going to do row operations such that x2 appears only in the third constraint row with a coefficient of 1. So we're increasing x2 all the way to 3. The new value of x2 is determined by constraint 3. So do row operations such that x2 appears only in constraint 3. Only in constraint 3. Let me write constraint 3 again here. With a coefficient of 1 and nowhere else. Great. Let's do those row operations. I want x2 to appear only in this constraint row with a coefficient of 1, and nowhere else. I want x2 to appear only in the third constraint row with a coefficient of 1 and nowhere else. Let's do those row operations. I want x2 to disappear from the objective function row, which means that multiply the third constraint row by -7, add it to the objective function row. I want x2 to disappear from the first constraint row, multiply the third constraint row by 8, so that 1 over 4 times 8 is going to be 2, and there's a -2 there. So multiply the third constraint row by 8, add it to the first constraint row. And I want x2 to disappear from second constraint row, multiply the third constraint row by -5, add it to the second constraint row so that x2 disappears from the second constraint row. Let's do these row operations. Multiply the third constraint row by -7 and add it over here. x1 times -7, -7x1 plus 0x1, -7x1. 1 over 4 x2 times -7, -7 over 4 x2 plus 7 over 4 x2, x2 goes away. -1 over 4 x3 times -7 plus 7 over 4 x3 plus another 1 over 4 x3, 1 over 4 plus 7 over 4, 8 over 4, that is a 2x3. No w1, no w1, no w1 here. No w2, no w2, no w2 here. 1 over 4 w3 times -7, -7 over 4 w3. Another -5 over 4 w3. So that's -12 over 4 w3. That is a -3 w3. What do we have on the right-hand side? 3 over 4 times -7. That is -24 over -21 over 4. Plus another 15 over 4. That is going to be -36 over 4. That is a -9. Good. Let's take care of the first constraint row. Multiply the last constraint row by 8. Add it to the first constraint row. x1 times 8, 8x1 plus no x1. That is 8x1 here. 1 over 4 times x2 times 8. That is going to give me 2x2 minus 2x2. x2 disappears. That's what I'm trying to do. Minus 1 over 4 x3 times 8. That is minus 2x3 plus another 2x3, x3 disappears here. No W1 times 8, no W1 plus another W1, W1 here. No W2 plus no W2, there's no W2 here. W3, 1 over 4 W3 times 8, 2 W3, minus another W3 plus W3. And on the right-hand side, 3 over 4 times 8, 3 over 4 times 8, that is a 6, plus another 3, that is a 9 on the right-hand side. Let's keep going. Let's take care of the second constraint row. Multiply the third constraint row by -5, add it to the second constraint row. Multiply the third constraint row by -5, add it to the second constraint row. x1 times -5 is -5x1 plus 0x1, that is a -5x1. 1 over 4 x2 times -5 is -5 over 4, plus another 5 over 4, x2 goes away, that's what we want. Minus 1 over 4 times -5 x3, that is plus 5 over 4 x3, plus another 7 over 4 x3, that is 12 over 4 x3, that is a 3x3. Let's keep going. 0w1 plus 0w1, no w1. 0w2 times -5 is 0w2, plus another w2. That's just w2. 1 over 4 w3 times -5 is -5 over 4 w3. Another -3 over 4 w3, -5 over 4, -3 over 4, that is -8 over 4, that is a -2 w3. And on the right-hand side, 3 over 4 times -5 is -15 over 4, plus another 27 over 4. 27 minus 15 is 12, 12 over 4, that's a 3 on the right-hand side. And lastly, we want x2 to appear in this constraint row with a coefficient of 1. So let's multiply this whole constraint row by 4 so that x2 appears in the last constraint row with a coefficient of 1. 4x1 plus x2 minus x3 plus w3 equals 3. Okay, good. Good. This is the new system of equations we reach. Do we have 3 decision variables, each appearing in a different constraint row with a coefficient of 1 and nowhere else? Yes. What are they? W1, W2, W3. So then what is the solution we read from to the system of linear equations? W1 equals 9, W2 equals 3, and x2 equals 3, and x1, x3, and W3 are 0. If x1, x3, and W3 are zeros, we should set z is equal to 9. In the previous iteration, our objective value was 15 over 4. Now we increase the objective value to 9. So we're making progress. Okay. So we ask ourselves, is there a decision variable that we can increase to make the objective function better? X1 doesn't give me any increase in the objective value because it's got a negative coefficient. W3 doesn't give me an increase in the objective value if I increase it because it's got a negative objective function coefficient. But if I increase x3, then the objective function is going to go up. For each unit of increase in x3, the objective function is going to go up by 2 units. So we're going to go ahead and increase x3. And the question is, how much can we increase x3 before we violate the feasibility of the solution that we have on hand? From the perspective of the second constraint, x3 does not even appear. From the perspective of the first constraint, x3 doesn't even appear in the first constraint. So as a result, from the first constraint, I can increase x3 as much as I want without turning W1 negative. So the first constraint doesn't give me any trouble. From the perspective of the first constraint, can increase x3 as much as we want without W1 turning negative. Good. What's happening in constraint 2? We're increasing x3. Right now, x3 is 0, W2 is equal to 3. As I increase x3, I'm going to eat up for the increase x3 by playing around with W2. Right now, this is 0, this is 3. If I increase x3 to 1, this is going to be 3. W2 has to go down to 0 so that they add up to 3. And if I increase x3 anything beyond 1, let's say 1.1, this is going to be 3.3. Then W2 has to be equal to minus 0.3 to make sure that they add up to 3. So then the largest I can increase x3 before W2 turns negative is 3 over 3, that's a 1. So from second constraint, we can increase x2, we can increase x3 up to 3/3, which is 1, before W2 turns negative. And what's happening in the third constraint? Let's again pay attention to this. I'm increasing x3. Currently, x3 is equal to 0, and x2 is equal to 3. I'm increasing x3. And I'm going to make up for the increase in x3 by playing around with x2. Right now, this is 0, x2 is equal to 3. If I increase x3 to 5, then it's a minus 5. Then x3 becomes 8, so that 8 minus 5 is equal to 3. If I increase x3 to 10, minus 10, so x2 has to be equal to 13, so that they are up to 3. If I increase x3 to 60, so that this is minus 60, x2 has to be equal to 63, so that 63 minus 60 is going to be equal to 3. If I increase x3 to 1000, so that this is minus 1000, x2 has to be equal to 1003, so that 1003 and minus 1000 is going to equal me a 3. So now from perspective of the third constraint, I can increase x3 as much as I want without the danger of x2 turning negative. Again, that's because x3 has a negative coefficient in this constraint. So from perspective of the third constraint, can increase x3 as much as we want without x2 turning negative. So constraint 1 says you can increase x3 as much as you want. Constraint 3 says you can increase x3 as much as you want, but constraint 2 says you can increase x3 all the way up to 1 only. So the binding number occurs at the second constraint. So we're going to increase x3 up to 1. In this case, the mean value of x3 is going to be determined by the second constraint. So we're going to do row operation such that x3 appears only in the second constraint row with a coefficient of 1 and nowhere else. So the new value of x3 is determined by constraint 2. Do row operations such that x3 appears only in constraint 2 with a coefficient of 1 and nowhere else. Let's do that. I want x3 to disappear here with a coefficient of 1 and nowhere else. For x3 to disappear from the objective function row, I need to take the second constraint row, multiply it by minus 2/3 and add it to the objective function row so that x3 disappears from here. Likewise, if I want x3 to disappear from the third constraint row, I gotta take the second constraint row, multiply it by 1/3, add it to the third constraint row so that x3 disappears from the third constraint row as well. Let's do those row operations. Good. Minus 5 times, minus 5 times, minus 5 times, minus 2/3. That is going to give us 10/3x1, another minus 7. 10/3x1 minus 7. 10/3 minus 21/3. That is going to give us minus 11/3x1. Good. No x2 here, plus another no x2 here. There's not going to be any x2. 3 times x3 times minus 2/3, minus 2x3, plus another x3. x3 goes away. That's what we want. No w1 here, no w1 here, so we're not going to have any w1. w2 times minus 2/3, minus 2/3 w2, plus 0 w2, minus 2/3 w2, minus 2 w3 times minus 2/3, that is a 4/3 w3. Another minus 3, 4/3 minus 3, that is 4/3 minus 9/3, that is minus 5/3 w3. And what do we get on the right-hand side? 3 times minus 2 over 3, that is going to give us 3 times minus 2 over 3, that's going to give us minus 2. Another minus 9 over here, z minus 11. We took care of the objective function row. In the first constraint row, x3 doesn't appear at all, so I can write the first constraint row as it was. Good. And I want x3 to disappear from the third constraint row as well. Multiply the second constraint row by 1/3 and add it to the third constraint row. Minus 5x1 times 1/3 minus 5 over 3 plus another 4. 4 minus 5 over 3. So that's 12 over 3 minus 5 over 3. That's a 7 over 3 x1. 0x2 times 1 over 3 is 0x2 plus another x2. That is an x2 here. 3x3 times 1 over 3 is 1x3 minus an x3. x3 disappears. That's what I'm trying to do. 0w1 times 1/3 is 0w1 plus 0w1, 0w1 here. 1/3 times w3 is 1/3 w. I'm sorry, 1/3 times w2 is 1/3 w2 plus 0w2. That's going to give me 1/3 w2 here. Minus 2 times 1 over 3 w3 minus 2 over 3 w3 plus another w3. 1 minus 2 over 3, that's going to give us 3 over 3 minus 2 over 3, that's going to give us 1 over 3. W3. And on the right-hand side, 3 times 1/3 is 1, plus another 3, that's a 4. And I want x3 to appear in the second constraint row with a coefficient of 1. So multiply the second constraint row by 1/3 across, so that x3 appears in the second constraint row with a coefficient of 1. Good. Okay. Do we have 3 decision variables? This is the next system we reach. Do we have these 3 decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else? Yes. Okay. So now let's read the solution from the system of linear equations. W1 equals 9, x3 equals 1, x2 is equal to 4, x1, w2, and w3, x1, w2, and w3 are all 0. If x1, w2, and w3 are 0, this is 0, z has to be equal to 11. Excellent. So now this is the system of linear equations we reached. Again, we ask ourselves, can we make the objective value better? Can I get to a better objective value? If you look at the objective function row, for each unit of increase in x1, the objective value goes down by minus 11 over 3. For each unit of increase in w2, the objective value goes down by minus 2 over 3. For each unit of increase in w3, the objective value goes down by minus 5 over 3. So there is no decision variable that if we can increase to make the objective value larger, then we can conclude that this solution that we reach is optimal to the linear program that we saw. Okay. So the optimal solution is, let's write x1, x2, x3, w1, w2, w3. x1 is what? 0. x2 is what? 4. x3 is what? 1. w1 is equal to 9. w2 is equal to 0. w3 is equal to 0. And to emphasize that this is optimal, let's put stars here. So the optimal solution to the LP is x1, x2, x3, w1, w2, w3. x1 is 0. x2 is 4. x3 is 1. w1 is 9. w2 and w3 are 0 is the optimal solution. With the optimal objective value, (11). And you can plug this solution into the objective function, see that that's also going to give us an 11. Right over here, x1 is 0, x2 is 4, and x1 is 1. 0, 3 times 4 is 12, minus 1, that's an 11. Good. So we solved the linear program. But again, as we did this, we saw one interesting case. If a decision variable appears, if you're increasing a certain decision variable, and if that decision variable has a negative coefficient in some constraint, then from the perspective of that constraint, you can increase that decision variable as much as you want without getting into trouble. If we're increasing a certain decision variable to get to a better objective, and if that decision variable has a negative coefficient in a certain constraint, then from the perspective of that constraint, you can increase that decision variable as much as you want without getting trouble. Okay, good. So now this is our second example. This is our second example to see the mechanics of the simplex method. And we're gonna, again, do these mechanics over and over again. Over time, you're going to get very, very comfortable with the mechanics of the simplex method. Okay, so to wrap this up, let's talk about the vocabulary of the simplex method. Because again, when people use the simplex method, they use this common vocabulary. It's nice to have access to, it's nice to speak that common vocabulary. So let's say that we have a linear program with n constraints and n decision variables. Say we have NLP, a linear program, with m constraints and n decision variables. Great. What we do is we add a slack variable for each one of these constraints. When we add the slack variables, we're going to have n plus m decision variables. Okay, so our linear program had m constraints and n x decision variables. Then we add the slack variable, we add a slack variable w for each one of these constraints. So when we add our slack variables, we're going to have n plus m decision variables, including the constraints. So we add m slack variables. These are my w's. In this case, RLP has m constraints and m plus m decision variables, including the slack variables. But if I have a linear program with m constraints and n decision variables, after I add up the slacks, after I add up the slack variables, we're going to have m constraints and n plus m decision variables. But during the course of the simplex method, there are always 3 decision variables such that each one, during the course of the simplex method, if I have m constraints, during the course of the simplex method, there are going to be m decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else, right? So if I have m constraints, then during the simplex method, there will always be 3 m decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1. If we have m constraints, then at each iteration of the simplex method, we will have m decision variables, each appearing in a different constraint row with a coefficient of 1. These are decision variables that can take positive values, and we call these decision variables as basic variables. So each one of these m decision variables that appears in a different constraint row with a coefficient of 1, they're called basic variables. The remaining n decision variables are called non-basic variables. If I have a total of n plus m decision variables, m of them are basic, so the remaining n decision variables are called non-basic variables. Let's do an example to understand what basic variables are, what the non-basic variables are. Let's look at the first iteration of our simplex method. Here's the first iteration. What are the three decision variables such that each one of them appears with in a different constraint or with a coefficient of 1? Nowhere else. W1, W2, W3. So those are the basic variables. And the remaining ones are called the non-basic variables. Let's look at our simplex method in the second iteration. Let's look at the simplex method in the second iteration. What are the three decision variables such that each appearing in a different constraint or with a coefficient of 1? W1, W2, X1. Those are my basic variables. Those are the variables that can take positive values. And the remaining ones are my non-basic variables. Non-basic variables always take value 0. Good. Let's do one more iteration if you like. Let's look at the third iteration. What are the decision variables? What are my three decision variables, each appearing in a different constraint or with a coefficient of 1, W1, W2, and X2? Those are basic, and these are non-basic. Only basic variables can take positive values. Non-basic variables always have to take values 0. Good. So this is basic versus non-basic. Great. So let's introduce one more terminology. At each iteration of the simplex method, we take one non-basic variable and start increasing its value. Okay? At each iteration of the simplex method, we take non-basic variable, start increasing its value. That non-basic variable that we start increasing its value becomes basic at the next iteration. So we call that variable as the entering variable. Let's say again, at each iteration of the simplex method, we take non-basic variable, we take one non-basic variable and start increasing its value. That non-basic variable at the next iteration becomes basic. So we call that variable that goes from non-basic to basic as the entering variable. At each iteration of the simplex method, we take one non-basic variable and start increasing its value. That variable is called the entering variable. This variable becomes basic at the next iteration. Good. In response to the entering variable, in response to the non-basic variable becomes basic, one variable that was basic at the current iteration becomes non-basic at the next iteration. And that variable is called the leaving variable. In response to the entering variable, one variable that was basic at the current iteration becomes non-basic at the next iteration. And that variable is called the leaving variable. Good. So now again, let's look at the iterations of our simplex method and let's identify the entering and leaving variables. This is the first iteration. What is the non-basic variable whose value we're increasing? What is the non-basic variable whose value we're increasing? X1. So in this iteration, the entering variable is X1. Good. So now, in response to this entering variable, one variable that was basic in this iteration is going to be non-basic at the next iteration. Here's the next iteration. What is the basic variable that was basic at this iteration becomes non-basic? What is the variable that was basic at this iteration becomes non-basic at the next iteration? W3. W3 at the next iteration is not basic anymore. So then W3 is leaving. Okay. Another way to identify the leaving variable is that as I increase X1, which constraint is binding to determine the value of X1? It was a third constraint that determines the value of X1 as I increase X1. So as a result, at the next iteration, the basic variable corresponding to the third constraint is going to be leaving. That is, the basic variable corresponding to the third constraint at the next iteration is going to be non-basic. So the leaving variable is the basic variable corresponding to the third constraint. Okay. So let's look at the second iteration of our simplex method and identify the entering and the leaving variables. In the second iteration of my simplex method, what is the non-basic variable whose value we're increasing? We're increasing the value of x2. So the entering variable is x2. x2 is entering. Good. In response to the x2 entering, what is the variable that is basic now becomes non-basic at the next iteration? Again, x2 is entering. What is the constraint that is determining the value of x2 at the next iteration? That is constraint 2. As a result, the basic variable corresponding to constraint 2 is going to be leaving. So x1 is leaving. And indeed, if you look at the next iteration of our simplex method, these are my current basic variables. At the next iteration, x1 is not basic anymore, so x1 left. Let's look at the third iteration of our simplex method. What is the entering variable? Which non-basic variable we're increasing? We're increasing the value of x3. So x3 is entering. In response to x3 entering, which basic variable is leaving? Well, let's look at which constraints determines the value of x3. The value of the second constraint is determining the value of x3. So that means that in the next iteration, the basic variable corresponding to the second constraint is not going to be basic anymore. So W2 is leaving. And if you actually check the simplex, if you actually check the system of equations at the next iteration, these were my current basic variables, W1, W2, X2. At the next iteration, W2 is not basic anymore, so W2 left. Okay, so this is the concept of entering and leaving variables. Great. So we can wrap this up here. We saw one more example on which we kind of got more comfortable with the mechanics of the simplex method. And we saw one nice little cute thing. If we're increasing a non-basic variable, and if the coefficient of that non-basic variable in some constraint is negative, then from the perspective of that constraint, we can increase that variable as much as we want without getting in trouble. And lastly, we learned some terminology about the simplex method, which is the basic variables, non-basic variables, entering variables, and the leaving variables. Okay, good. So that's a good point to stop.